In this chapter, I will discuss motion in 2 and 3 dimensions. Here we are going to combine what we've learned so far about motion in 1 dimension and also vectors. So first let's define the position of a particle in 3-dimensional space. The position vector can be written in unit vector notation as shown here. In general, the position vector we will label with r, and in unit vector notation that will be x I hat plus y j hat plus z k hat. So for example, the position vector that defines a point with coordinates -3 meters, 2 meters, and 5 meters is shown in the figure right here. So this is the position vector r with an x coordinate -3 meters right here, a y coordinate 2 meters right here, and a z coordinate of 5 meters right here. So in the terminology of vectors, these coordinates are also known as the components of the vector. So how do we find the components of the vector? If we know the geometry of the problem, like shown in this drawing. Well, if this is my point in space and this is the position vector, all I need to do is do perpendicular projections into the 3 different planes and then intersect those with the coordinate axis to find the actual coordinates. And so, for example, if from this point I do a perpendicular projection into the xz plane, so this plane right here, and then intersect with the x-axis, that gives me the x-coordinate. Then if I intersect with the z-axis, that gives me the z-coordinate. And then if I look at this perpendicular towards the xz plane, that is that determines the coordinate in the y direction. So now we are ready to define displacement in general 3-dimensional space. The definition is just an extension of the definition that we had for 1-dimensional problems. That definition was that the displacement was equal to the final position minus the initial position. So again, this was a 1-dimensional definition. Here the definition is 3-dimensional. So the displacement vector is a 3-dimensional vector and the 2 position vectors are 3-dimensional vectors. So how do we find the displacement vector using the components of the 2 position vectors? Well, simply we are going to subtract the x components of the 2 position vectors, the y components, and the z components of those vectors. And so the difference in x components I hat is the x component of the resultant vector, so we can call it delta x. And then the difference in the y components of the 2 position vectors will be delta y, and similarly the difference in the 2 z components of the 2 position vectors will be delta z. And so the displacement vector is the sum of the individual displacements along each coordinate direction. Or in other words, delta r is equal to delta x I hat plus delta y j hat plus delta z k hat. Now let's also expand the formalism in 3 dimensions to define average velocity. So as a reminder, the average velocity in 1 dimension was defined as the displacement divided by the elapsed time. And so here we just expand the definition to include a 3-dimensional displacement. So the average velocity becomes the displacement in 3 dimensions divided by the elapsed time. And so if I replace delta r here with its equal from the previous page. The average velocity becomes delta x I hat plus delta y j hat plus delta z k hat, all of that divided by delta t. And so I can split this into the sum of three terms, delta x divided by delta t I hat plus delta y divided by delta t j hat plus delta z divided by delta t k hat. And now, based on the definition of average velocity, you can also recognize that each term here corresponds to the average velocity in each coordinate direction. So here we have the average x, this is the average y, and this here is the average z. So these are the components of the average velocity in x, y, and z direction. And so here's a simple example of this concept. So we have a particle that moves through a displacement of 12 meters I plus 3 meters k for a time of 2 seconds. So the average velocity then is the displacement divided by the time. So that's 12 meters I plus 3 meters k divided by 2 seconds, or that is 6 meters per second I plus 1.5 meters per second k. And so this first term here, this is the average velocity component in x direction, and this second term here, this is the average velocity component in z direction. And so since the displacement did not have a component along the y coordinate axis in y direction, then the average velocity does not have a y component as well. Now let's define instantaneous velocity in 3 dimensions as well. The velocity of a particle at a single point in time is the instantaneous velocity. Instantaneous velocity is defined as the limit of the average velocity as the time interval shrinks to 0. And we write this as the instantaneous velocity v is equal to d dt of the position vector at that particular instance of time r. Remember, this is a 3-dimensional vector. So if we were to visualize the displacement in space for a moving particle in a 2-dimensional situation, in an xy coordinate system, the trajectory of motion is given by this brown line, and the position of the particle as it moves with those two position vectors r1 and r2. And then the displacement is the straight line difference between the two positions, that is delta r, the vector that delta r, that is the displacement. Okay, so the instantaneous velocity is the velocity of the particle as it moves along its trajectory at any moment of time. And so at any moment of time, the instantaneous velocity is tangent to the trajectory. And so because this is a 2-dimensional motion, the instantaneous velocity has 2 components. It has an x component and a y component. If the motion was 3-dimensional, then the instantaneous velocity will have also 3 components. It will have an x, y, and z components. And so it is very important to remember that the direction of the instantaneous velocity v of a particle is always tangent to the particle's path at the particle's position. And so in unit vector notation, the instantaneous velocity can be written as v is equal to d dt of the position function, which will be xi hat plus yj hat plus zk hat. And so if I distribute the derivative to all these 3 terms, we get dx dt I hat plus dy dt j hat plus dz dt k hat. And so in the first term, dx dt is the x component of the instantaneous velocity, so this is vx. The second term, dy dt, is the y component of the instantaneous velocity, vy. And then in the third term, dz dt is the z component of the instantaneous velocity, vz. And so v is equal to vx I hat plus vy j hat plus vz k hat. It's important to also notice that the velocity vector does not extend from one point to another. It only shows direction and magnitude. Now let's do, as an example, the following problem. A rabbit runs across a parking lot on which a set of coordinate axes has, strangely enough, been drawn. The coordinates in meters of the rabbit's position as a function of time, which is measured in seconds, are given. So the x-coordinate is given with this function, and the y-coordinate is given with this function. At t equal 15 seconds, what is the rabbit's position vector r in unit vector notation and in magnitude angle notation, so in polar coordinates? So to find the position of the rabbit at that particular moment of time, I simply need to substitute t with 15 seconds in the two functions and find the what are they equal to. So the x-coordinate at time t equal 15 seconds is equal to 66 meters, and the y-coordinate at the same moment of time is negative 57 meters. And so then the position vector is defined as a function of time, is defined as the x-coordinate as a function of time I hat plus the y-coordinate as a function of time j hat. I just calculated those two coordinates for that specific moment of time, 15 seconds. And so then the position vector is equal to 66 meters I hat minus 57 meters j hat. And so this is the position of the rabbit on the parking lot at 15 seconds. So this is unit vector notation. We are also asked to show the displacement in magnitude angle notation, so polar coordinates. So that means find the magnitude of the position vector and orientation in space. So to find the magnitude, we simply take the square root of the squares of the sum of squares of the two components. So square root of x squared plus y squared, which then becomes square root of 66 meters squared plus negative 57 meters squared. When you calculate that, it should give you 87 meters. And then for the orientation in space, the angle theta is equal to the inverse tangent of y divided by x. And so this will be equal to the inverse tangent of minus 57 meters divided by 66 meters. The units cancel out, and so the final result is negative 41 degrees. So let's sketch the vector to see where that angle is. So in the parking lot coordinate system, this is, actually let's do it this way. This is the y-axis, this is the x-axis, and so we can see that the vector has a positive x-coordinate, negative y-coordinate. So actually my coordinate system there is not done quite right, so let's redo it again. So we have positive x-axis here, positive y-axis here. So the resultant vector is in the fourth quadrant right here. There you go. So this is the position vector of the rabbit at 15 seconds. And the angle that was measured there, or that we calculated right here, negative 41 degrees, is the angle measured from the positive x-axis in clockwise direction. So 41 degrees in clockwise direction, and that's why we get the minus. Let's do one more example related to the previous problem. So for the rabbit in the preceding example, or sample problem, find the velocity at t equal to 15 seconds. From the definition of instantaneous velocity, we know that the instantaneous velocity is d dt of x I hat plus d dt of y j hat plus d dt of z k hat. This is a two-dimensional problem, therefore the third term in the velocity vector actually does not exist. So we don't have a third term, we only have the two terms, one along the x-axis and one along the y-axis. Okay, we have an expression for the position functions along the x and y-axis for the rabbit. Let's put them down on the board. So the position function along the x direction is negative 0.31 t squared plus 7.2 times t plus 28. And the position along the y-axis is 0.22 t squared minus 9.1 times t plus 30. So in order to get the instantaneous velocity, I must take the time derivative of the position function along each coordinate axis. And that's going to give me the coordinates or the components of the instantaneous velocity along those directions. So Vx is going to be equal to the x of t dt, which is d dt of negative 0.31 times t squared plus 7.2 times t plus 28. And so this gives me minus 0.62 t plus 7.2. And then for the y component, Vy, that will be dy of t dt. So that's going to be d dt of 0.22 times t squared minus 9.1 times t plus 30, which gives me 0.44 times t minus 9.1. So now I can calculate what those velocities are at 15 seconds. So Vx will be equal to minus 0.62 times 15 plus 7.2, and that gives me negative 2.1 meters per second. And Vy will give me 0.44 times 15 minus 9.1, and this is equal to minus 2.5 meters per second. And so finally, the velocity vector, the instantaneous velocity, will be equal to minus 2.1 meters per second I hat plus minus 2.5 meters per second j hat. Now I can also find the magnitude of the velocity. So the magnitude is square root of Vx squared plus Vy squared. And so this will be a square root of minus 2.1 meters per second to the second power plus minus 2.5 meters per second squared. And that is equal to 3.3 meters per second. And then the angle, or the orientation, is the inverse tangent of Vy divided by Vx. So this is the inverse tangent of minus 2.5 meters per second divided by minus 2.1 meters per second. This is equal to negative 130 degrees. And so if I draw the velocity vector in an xy coordinate system, let's do it right here, you can see from the two coordinates or components that this vector is going to be in the third quadrant. So this is my y-axis, this is my x-axis, so the vector is somewhere here, and the angle is this angle, 130 degrees, measured from the positive x-axis in clockwise direction, so minus 130. The concept of average acceleration and instantaneous acceleration naturally follows from the definitions of average velocity and instantaneous velocity. The average acceleration is calculated as the change in velocity divided by the elapsed time, or that is delta v divided by delta t, where now delta v is in general three-dimensional vector. And the definition of instantaneous acceleration is achieved from the definition of average acceleration when we take the limit where the time approaches zero. Instantaneous acceleration is equal to dv dt. But we have an expression for the velocity as a function, for the velocity vector as in a unit vector representation, right here. So then we can express the instantaneous acceleration as the sum of three terms, one along each coordinate direction. So the instantaneous acceleration is d dt of vx I hat plus vy j hat plus vz k hat, or this is dvx dt I hat plus dvy dt j hat plus dvz dt k hat. And so again, you will notice that the Vx dt is simply the x component of the acceleration, the Vy dt is simply the y component of the acceleration, and the Vz dt is simply the z component of the acceleration. And so the acceleration vector can be written in unit vector notation as a is equal to ax I hat plus ay j hat plus az k hat. And so, for a particle moving in an x and y coordinate system in two dimensions, the trajectory is shown with the brown line. And so the acceleration is directed in a certain direction, but is the sum of its two components, the x component and the y component. So let's do another example, this time calculating the acceleration for the rabbit in the previous two examples. Let's calculate the acceleration at t equal 15 seconds. So by definition, the instantaneous acceleration is dvx dt I hat plus dvy dt j hat plus dvz dt k hat. In our particular example, the acceleration is two-dimensional, so the third component here is equal to 0. And so then I must find the derivatives with respect to time of the x component and y component of the instantaneous velocity. And so the x component is equal to ddt of minus 0.62t plus 7.2, which gives us minus 0.62 meters per second squared. And for the y component of the acceleration, we have ddt of 0.44 times t minus 9.1, or this is 0.44 meters per second squared. And so then in unit vector notation, the acceleration, the instantaneous acceleration, is equal to minus 0.62 meters per second squared I hat plus 0.44 meters per second squared j hat. Now let's find the magnitude of the acceleration vector. The magnitude of the acceleration vector is square root of ax squared plus ay squared. So this is a square root of minus 0.62 meters per second squared to the second power plus 0.44 meters per second squared to the second power. And so this is equal to 0.76 meters per second squared. The direction of the acceleration is given by the angle theta, which is the inverse tangent of ay divided by ax, or this is the inverse tangent of 0.44 meters per second squared divided by negative 0.62 meters per second squared. This is equal to negative 35 degrees. So let's sketch this vector in xy coordinate system. As you can see from the two coordinates, we have negative x coordinate and positive y coordinate, so that means that the acceleration is in the second quadrant. So here is my y-axis, here is my x-axis, and the acceleration vector is in the second quadrant. And so the angle that we've calculated here, negative 35 degrees, is the angle measured from the negative x-axis, 35 degrees. If we wanted to measure the angle from the positive x-axis, then we do 180 plus negative 35. So that will be this angle, and that will be 145 degrees. Now let's discuss two specific types of multidimensional motion: projectile motion and uniform circular motion. Let's start with projectile motion. A projectile is a particle that is moving in the vertical plane with some initial velocity, with acceleration that is always equal to the free fall acceleration g. The motion of a projectile is called the projectile motion. So here is a two-dimensional coordinate system, x and y. A projectile launched in air will follow a trajectory that has this shape, that's the shape of a parabola. The acceleration that this projectile will always experience is the acceleration due to gravity, which always points towards the ground. The value is 9.8 meters per second squared. The initial velocity of the projectile we will call v. Has two components. Has an x component, vx, and it has a y component, vy. So v is equal to vx plus vy added as vectors. And if I use unit vector notation, v is equal to v. Actually, let's call the initial velocity v0. So v0y, v0x. So v0 is equal to v0x, v0 plus v0y. So v0 will be equal to v0x I hat plus v0y j hat. So what are those two components, v0x and v0y, in terms of the magnitude of the initial velocity v0? Well, let's assume that the angle that the projectile makes with the horizontal axis is theta. And so then v0x is equal to v0 cosine of theta, and v0y is equal to v0 sine of theta. And so one more time, the initial velocity v0 of the projectile is equal to v0x I hat plus v0y j hat, where v0x is equal to v0 cosine of theta and v0y is equal to v0 sine of theta. So an important property of projectile motion is that the vertical and horizontal components of the motion are independent of each other when it comes to the velocity of motion and acceleration. Where the two are connected is the time for the motion. Both portions take the same amount of time. And so in projectile motion, the horizontal motion and the vertical motion are independent of each other. That is, neither motion affects the other. And so it's been shown experimentally that that is the case. Here is an example of a stroboscopic, here's an image of an experiment where a stroboscopic image was taken of the motion of two identical spheres colored in different colors. The red one dropped straight down towards ground, while the yellow one was shot forward and then went to ground. Both spheres again were identical, both were released at the same time. As you can see from the image, it took the same amount of time for both to hit the ground. And so if you consider the motion of a projectile, as you can see, the shape of this trajectory consists of vertical motion starting from ground level and going all the way up at the top, while at the same time the object is moving horizontally. So if the object was not in motion horizontally, then the projectile will be just moving up and down in the air, straight up and down. Now, if you stretch the motion horizontally as well, if the projectile is moving horizontally, then at every moment of time there is a slight shift in position horizontally as well as vertically. And so if we take a stroboscopic image of the trajectory, it will look like so. So we have independent motions in the vertical direction and horizontal direction, in the sense that they do not affect each other. So then what is the difference between the two components of the motion, between the horizontal and the vertical component? The horizontal motion is a motion without acceleration. So the motion is with constant velocity. The displacement horizontally is equal to the initial velocity in x direction times the time of travel. Or in other words, the horizontal displacement is equal to v0 cosine of theta times t. For the vertical part of the motion is happening with constant acceleration, and that is the acceleration due to gravity. That means that for the vertical part of the motion, I can apply the formulas that we derived for the kinematics of moving objects in vertical direction. We're adjusting for the direction of the gravitational acceleration gives us the following set of formulas. For the vertical displacement, we have v0y times t minus 1/2 gt squared, or if I substitute v0y with its relationship to the initial velocity v0, that is v0 sine of theta times t minus 1/2 gt squared. Then for the vertical velocity, we have the final vertical velocity is equal to the initial velocity sine of theta minus gt. And then we also have that vy squared is equal to v0 sine of theta to the second power minus 2 times g y minus y0. So this first term here is the initial velocity in y direction, and this difference here is the vertical displacement. So let's summarize those results on this slide. So the horizontal motion happens with acceleration ax equal to 0. And so because of that, the horizontal displacement x minus x0 is equal to v0 x times t, which is also v0 cosine of theta times t. For the vertical motion, the acceleration ay is equal to negative g. And so here we have several different kinematic equations that can be applied. So the vertical displacement y minus y0 is equal to v0y times t minus 1/2 gt squared, which becomes v0 sine of theta times t minus 1/2 gt squared. Then we have vy is equal to v0y minus gt, which becomes v0 sine of theta minus gt. And finally we have vy squared is equal to v0y squared minus 2 times g y minus y0, which becomes v0 sine of theta squared minus 2 times g y minus y0. So this is the set of three kinematic equations that are used to define the motion or calculate parameters of the motion in the vertical direction. Note here regarding the value for g. Since I already accounted for the direction through the change of signs in all these formulas, the value that you use for g here, here, and here will be 9.8, not negative 9.8. I already stated that the trajectory of the projectile is a parabola. The equation that can calculate the trajectory is given with this formula. So y is equal to tangent of theta times x minus gx squared divided by 2 times v0 cosine of theta to the second power. The horizontal range is given as r equal to v0 squared divided by g sine of 2 times theta 0. The range has a maximum when the angle theta is equal to 45 degrees in the absence of air resistance. When air resistance is present, the maximum range is not at 45 degrees. The calculation for that is a little bit more complicated. One other important point to make: at the highest point of the parabola, or the trajectory, right here, the velocity v has only an x component. The y component is equal to 0. Also, when the projectile reaches ground level, so it starts from ground, reaches ground level again, the magnitude of the velocity with which the projectile hits the ground is equal to the magnitude of the initial velocity. What is different, obviously, is the direction of the velocity vector right here. It's at a different angle with respect to the horizontal, but the magnitude is the same. So let's sketch it with red. So the velocity right here, v, by magnitude is the same as v0. This angle here with the horizontal is by magnitude equal to that angle. The difference between the components for both velocities, the final and the initial, will be the x component remains the same because the horizontal motion is without acceleration. The vertical components will have opposite direction. The initial vertical component points up, the final vertical component points down. All of this is only true when the starting and landing points are on the same level. If there is difference in levels, then these statements are not true. Let's show some of these concepts with the following example. One of the most dramatic videos on the web supposedly shows a man sliding along a long water slide and then being launched into the air to land in a water pool. So the situation is shown in the figure below. Here's the water slide. The person is being launched in the air with initial velocity v0 like so. So they will fly through the air and will land in the water pool. So let's take the horizontal distance between the launch point and the water pool to be d equal to 20 meters. Let's take the time for the flight from the launch to until the person lands in the water pool be 2.5 seconds, and let's the launch angle be 40 degrees. So let's find the magnitude and the velocity at launch and landing. So for the initial velocity, we have v0 with components v0 x and v0 y. And then for the landing velocity, we will have v with components v0x, with components vx, which will be equal to v0x, because horizontally the motion is with constant velocity, so no change, and a vertical component of vy. And so this vector here is v. So what we're looking for is the two velocity vectors v0, which will be v0x I hat plus v0y j hat. And we are also looking for v, which would be vx I hat plus vy j hat. What we need to find are the components of those vectors. So let's start with the horizontal component of the initial velocity and also the final velocity. So again, the horizontal components are equal to each other. To find the component, I will use the horizontal part of the projectile motion. So we know that the horizontal displacement, which is equal to d in the figure, is equal to v0x cosine of theta times t. So I know the displacement, I know the angle, I know the time, so I can calculate v0x. So from here, v0x will be equal to d divided by cosine of theta t. So this is 20 meters divided by cosine of 40 degrees times 2.5 seconds. And so when you calculate that, that's going to give you 8 meters per second. So we found the x component of the initial velocity and also the x component of the final velocity. One more time, they're equal. So v0x is equal to vx. So now let's find the y component. We actually don't need to find the y component. Let's find the initial velocity. So I already know the x component of the velocity, and the relationship with the initial velocity is that v0x is equal to v0 cosine of theta. And so from here, v0 will be equal to v0x divided by cosine of theta. So I want to say that I made a mistake in the previous calculation right here. This does not contain cosine of theta. It is simply v0x times t. And so from here, v0x will be equal to d divided by t. So let's fix that. Divided by t, and then here we have 20 divided by 2.5 seconds. 2.5 seconds, and the result is correct. It's 8 meters per second. So then v0x is equal to v0 cosine of theta. From here, v0 is v0x divided by cosine of theta. So now that becomes 8 meters per second divided by cosine of 40 degrees. And this is equal to 10.4 meters per second. And so the initial velocity by magnitude, this vector here, by magnitude is 10.4 meters per second. So to find the final velocity, vector, magnitude, and direction in space, I already know the x component of that vector, but I need the y component of that vector. So to find the y component, I'm going to use one of the kinematic equations that are relevant for the vertical portion of the projectile motion. And so this relationship is that v0 is equal to the initial vertical velocity v0y minus gt. So this becomes v0 sine of theta minus gt. And so substituting the values that I know for all of these quantities, we have 10.4 meters per second times sine of 40 degrees minus 9.8 meters per second squared times 2.5 seconds. This gives me negative 17.78 meters per second. So this is the y component of the final velocity right here. Okay, so now I can find the magnitude of the final velocity vector v. And so the magnitude is square root of vx squared plus vy squared. So it's the square root of 8 meters per second squared plus negative 17.78 meters per second squared. This gives 19.5 meters per second. The direction of the vector is given as the angle theta equal to the inverse tangent of the y component divided by the x component. So that is the inverse tangent of negative 17.78 meters per second divided by 8 meters per second. That is negative 66 degrees. And if we sketch this vector from the coordinates, from its components, one being 8 meters, so this is the x component, and negative 17.78 meters, that is the y component. This is in the third quadrant. So let's sketch this. So this is the y axis, this is the x axis, and so the vector is somewhere here. And the angle actually the vector is not there, the vector is in the fourth quadrant. So let's fix that. Here we go. So the vector is somewhere here, and the angle is this one, theta equal to negative 66 degrees. Again, the minus sign is because the angle is measured from the positive x-axis, but in clockwise direction, in this direction of rotation. So here notice that the two vectors, the initial and the final, do not have the same magnitude. So the initial vector has a magnitude of 10.4 meters per second, and the final 19.5 meters per second. The reason for that is because the launch point of this projectile motion is not at the same level as the landing point. Because of the difference of levels, the two velocities are different in magnitude. The second type of multidimensional motion that I mentioned before was uniform circular motion. So a particle is in uniform circular motion if it travels around a circle or circular arc at constant speed. Since the velocity changes, the particle is accelerating. So what does that mean? So here is the velocity for this particle that goes around this circle. So the direction of the velocity changes at all times as the particle goes around the circle. However, the magnitude of the velocity, which is the speed, does not change. It remains constant. So the particle maintains constant speed. The velocity changes by direction, which then means that the particle is accelerating. So the velocity's magnitude remains the same. That only can happen when the acceleration with which this particle is moving is constant. If the acceleration wasn't constant, the magnitude of the velocity will be changing as well, not only the direction. So when only the direction is changing, that means that the acceleration is constant. It turns out that the direction of the acceleration is always towards the center of this circular trajectory. So at all moments during the rotation of this object, the acceleration that acts on the object is towards the center of this circle. Then what is the relationship between the acceleration of motion and the velocity of motion? Well, the relationship is given with this formula. So the acceleration is equal to the velocity to the second power divided by the radius of the circular trajectory. Because the acceleration points towards the center of this circle, it is called centripetal acceleration. So the centripetal acceleration is related to the velocity of motion as v squared divided by r, where r is the radius of that circular trajectory. And then I can also define a time for one full rotation around this circular trajectory. This time is called period of revolution. And so the period of one revolution is equal to the circumference of the circle or the circular trajectory divided by the speed of rotation. So 2 pi times r divided by v. Here is where we're going to stop with the consideration of uniform circular motion. In later chapters, we're going to expand those notions to include more concepts that are associated with that motion. Simply in terms of kinematic properties of two-dimensional or three-dimensional motion, knowledge of centripetal acceleration and period of motion is currently enough for the purposes of this chapter.